basically the before we break, we talk about hey, if you want the ammonia to be utilized as a fertilizer only, and then you can do that. It's very pretty cheap. It's very cheaper. You do not need pressure swing at absorption. You do not need cryogenic. All you need to do is just the sulfuric acid solution. Let's say if you can use the concentration 1 m sulfuric acid solution, and then when ammonia is dissolved, and then after that you just vaporize the water, then you have this powder, the fertilizer. It's ammonium sulfate. You can apply this to the in the farm's field right away. Okay. So anyway, so I just want to show you there's different way to handle this, but most of the ammonia plant they do not do this because you want to sell ammonia as as the chemicals. Ammonia, I think today it depends on season. So now is the winter season, the price is low. So when you get to the spring, let's say the February or the March time, when the farming started, it could be like over $1,000 per ton. So it's where the where the I would say the price is very much fluctuate ammonia. Anyway, I'm not gonna talk about this. And also I want to also mention about this graph. I want you to pay attention to the time. If a time stretch is too long, the desorption time is very bad. All right. So remember how you size the reactor. Today in the first session we talk about if you want to size the of the reactor. So what's important is remember is gram of ammonia and then per gram of the catalyst per hour. All right. Here is the same thing. It's if this hour is too long, and then the number is getting lower. All right. So the shorter the better. The shorter the higher the capacity. And then so anyway, so that's why this the raw data is very important. It helps you to design the absorber. Okay. Keep in mind the solvent I'm talking about here is called reactive adsorption using magnesium chloride. You can also put this magnesium chloride inside the reactor, not necessarily the downstream. All we are talking about here is putting the solvent after reactor because we want to adsorb ammonia and then so the hydrogen nitrogen recycled. There's another scenario. This basic square shape is called a reactor. You can put a solvent in the reactor. So what does it mean? Nitrogen, hydrogen come in, and when they come in, they ammonia, I'm talking about inside the reactor, they basically absorb on the solvent. So my question is, when that thing happen, ammonia absorb on the solvent inside the reactor, it's only nitrogen and hydrogen. All right. So I'm repeating. So you put this the orange color solvent inside the reactor, and then ammonia absorb on the solvent. So only thing you have is nitrogen and hydrogen. So before that, this is reach equilibrium. All right. So let me this reaction inside the reactor without solvent is in equilibrium. That means in the reactor you will have nitrogen, hydrogen, ammonia. So now you drag the ammonia on a solvent. What's happening? Does it help the equilibrium? Where's the equilibrium will shift? Anybody has any question? Get my question. So if you before you let me put it before you put a solvent in there, ammonia, hydrogen, nitrogen reach equilibrium. All right. So now you put a solvent in there. So the ammonia on the solvent. So what will happen to this ammonia synthesis reaction? Anybody want to give a try? So basically, it was here, all right? So with the solvent, they come to the solid. So that means ammonia will not contact with hydrogen and nitrogen. The reason they reach equilibrium because these three molecules, they basically all in the gas phase, and then in contact. That's why they reach equilibrium. So, and then now I'm dragging the ammonia onto the solvent. What's happening in terms of so how the equilibrium is affected by having ammonia on the solvent?
Hydrogen unstable.
Let's keep on going. So when ammonia is did you get this question? Ammonia is absorbed on the solvent inside the reactor. And how does this affect equilibrium position?
Pressure will be created inside the reactor.
Yeah? How does it affect the equilibrium position? Okay, I'm continue. Okay, so I'm gonna looks like I don't think the audience has any knowledge on the chemical equilibrium. So let me simplify my question. Okay. So remember we calculated conversion the other day, all right? Of ammonia is 10%. Okay. So before solvent is added to the reactor, okay? So I would say before this, okay? The equilibrium conversion is 10%.
Why? Okay.
Just read my question, okay? I'm gonna.
It will be settled on the solvent layer.
So it makes sense, all right? So now I'm putting it back. So the first question before that, okay, is before, and then after. Will the conversion solvent, will the conversion go up or down? It's called a equilibrium position change. Someone say go up, all right? Yes. Why? That's called the equilibrium change. Why it goes up?
Because solvent will absorb the excess nitrogen present ammonia.
Okay, that's one reason. So what's another reason? If you just look at this yellow.
It will be gaseous state, so it will directly go to the solvents.
So basically, if you learn high school chemistry, the chemistry teacher will tell you, if you remove product, I'm talking about remove product, equilibrium will shift to the right, all right? Did high school the teacher tell you this? Do you remember this? Does high school the chemistry teacher teach you this? Removing product from the reactor, equilibrium will shift to right.
Reversible.
Is it correct? Yes or no?
Yes, sir. It will be reversible.
Okay, that's what I mean. So that's why I spend so much time to write the equation. I want to come to the point. So this is basically when you add a solvent in there, you remove the ammonia from the product. That's why you only see nitrogen and hydrogen. So that's why I give you the good example. Before you adding solvent, you 10%. After you add solvent, I think the answer, some answer is correct. It's greater than 10%. What's the interpretation? I know you say the nitrogen hydrogen partial pressure increase. That's correct. Nitrogen hydrogen partial pressure increase, but that's not the real reason. The real reason is the ammonia as a product got removed from the product, so the equilibrium. Oh, geez, I put it wrong. So equilibrium will shift this way. That's the direction. Okay. So if I show you another scenario, okay, what about on purposely I add ammonia in here? Okay, if you add ammonia, which means on the ammonia on the right, equilibrium will be shifting to the left. All right.
Yes,
So
sir.
because nobody add ammonia to the reactor. I'm just telling you, just in case you add ammonia into the reactor. So that means you don't do this. You increase ammonia, and the equilibrium will shift to the left. That means your conversion would be decreasing. Okay. All right. So let's come back to here. So now it sounds good. All right. So when you add a solvent in the reactor, equilibrium shift to the right, you have higher the conversion, greater than 10%, over 10%. What's the advantage of the reaction of reactive adsorption? This is called reactive adsorption. We already talk about increase conversion. All right. Any advantage of this? We will talk about disadvantage. And then what's the another one? Anything? Anybody can think something else? What's the advantage is? Keep in mind that you add a solvent in the reactor.
Gaseous and solid state is easy. Separation of gaseous state and solid state, liquid state is easy. Ammonia.
Make sense? Because you already have the ammonia and solvent inside the reactor. So what's coming out here? It's just nitrogen and hydrogen. There's no need to do the downstream separation. All right, is that that's advantage. All right. So coming out from here will be N2 and H2. All right. So there's no ammonia anymore. Ammonia actually are inside the reactor on the solvent. So no downstream separation. Or I would say the separation in the downstream. Do you agree? Say something. Do you agree with the solvent here? It's going to ease downstream separation because there's no need of the separation. I already separate ammonia inside the reactor. Make sense?
Yes, sir.
So basically increased conversion due to the shift of equilibrium position. Okay, so let's talk about disadvantage. What's the disadvantage you see here? Any disadvantage of this the configuration?
The carbon it will not.
Please repeat your question again. What did you say?
It will be partially only absorbed, not fully.
You are saying partially absorbed, all right? Is that what you say?
Yes, sir.
Thank you. So if partially absorbed, very good question, very good. So if partially absorbed, that means you still have NH, you still have ammonia come out, all right? Makes sense, all right? So it's not 100%, so you still have to come out. So that means you need not only solvent inside the reactor, you downstream also need it because it is partially adsorbed. That means you still need a very good, okay? Thank you. Keep on going. You still need downstream separation. Correct? Because advantage we say is separation in the downstream because I say disadvantage, if only partially adsorbed, you still need a downstream separation, all right? Because you want hydrogen nitrogen recycled, but not ammonia. So anything else? Let's pull out another one. So what's another disadvantage? Can you read my question? So what if the solvent is saturated?
It will absorb any ammonia, sir.
Yes. It will not adsorb any ammonia. Okay. So keep in mind, I put a solvent here. The reactor also have catalyst in there. Okay. So I'm going. So the ammonia synthesized reactor also have a catalyst in there. Okay. And that's solvent. So that means you have solvent, you have catalyst. When solvent is saturated, you need to regenerate it, all right? So that means you have to turn your reactor into the dissolver, all right? That means, what does it mean? You need a 2 reactor, at least, all right? So that's very expensive because your reactor was designed to do catalytic reaction, but not necessarily the separation because the separation was downstream. Now you put a solvent inside the reactor, sounds pretty cool because you increase the conversion, single pass conversion, and you ease downstream separation. But the downside of this, once it's saturated, and then you have to regenerate it. When you regenerate, you do the pressure swing, all right? So which means you have to put into another, put it on a standby and dissolve. You need a 2 reactor, just like this. Just like this. So, but a solvent dissolution without catalyst is very cheaper. It's very cheap. Okay, so you can afford to have 2 maybe 3 or 4, but having solvent and the catalyst in there, the catalyst is very expensive. Building 2 reactors to accommodate solvent regeneration is very expensive. So that's a disadvantage. Okay. Go ahead. Someone has a question. I'm gonna write it down. Okay. I'm writing. So you keep on talking. Go ahead. So do you see what I say? You need 2 reactors with a solvent. I would say containing solvent to do a swing operation. Make sense? So that means very expensive. They double your capital cost. So there's always trade-off. You solve one problem, you introduce another problem. So nothing is free. So there's a lot of advantage here, but there's a downside. Make sense? Any question before we move on to the next? Any question?
No, sir. No.
Okay, let's go to next. We haven't started economic yet. Okay, so I promise you, and the next couple slides we are going to start it. But let's talk about one more. Anyone has any question?
Yes, sir. If you use solvent layer, it will be more time consuming, sir. So
say it again.
If we use solvent layer, it will be more time consuming process, sir.
Oh, that disadvantage. You are talking about the basically if you do the swing operation, it's very time consuming. All right.
Sure.
Thank you. Yep. That's downside of it because times switching reactor is very consuming because you have to regenerate it. Thank you. Yeah, basically this translate into the operating cost. All right, that's the today we are talking about capital cost and operating cost increase. And then need 2 reactors. And then to do swing operation, I'm going to reduce the size of this, okay? To do swing operation, it's called a capital. So makes sense, all right? You need to write a capital expense goes up. If a time consuming operating cost goes up because you have to wait, all right? So all of techno-economic analysis we are going to talk about the next is all related how much capital cost, how much operating cost, okay? So you remember this curve. If you have this curve, you know, this is very important, dissolution time too long. That means you have to have big absorber to sit in there. That means you have to wait for so long to the basic switching them around. It's all add up to the cost of capital and then operating cost. Okay, so the shorter the better. That means the shorter the dissolution time, the better. The longer basically costs you a lot of money. Okay, so last separation before I show you the result from TEA, and then is membrane separation. You can separate the membrane. Membrane also called the molecular sieve. All right. So you have 3 molecules: hydrogen, nitrogen, and ammonia. So you want to separate using ammonia, control the size. So I'm going to block this. Here's a survey. Yeah, because there's answer in there. I don't want to see answer. I want to pick your guess based on the intuitive. So intuitively, I want you to tell me Can you read my question? Ammonia and hydrogen. Which one is larger?
Hydrogen will be higher, sir. Since the operating temperature is 500 degrees Celsius, separation of hydrogen is higher.
I'm talking about molecular size of the ammonia and hydrogen. I just want someone to guess, just based on your knowledge or intuitively, which one is larger molecular size? Just tell me quick answer.
Ammonia will be larger.
Thank you. Yes, I believe ammonia is larger. When I see the answer, but I mean when I tell, I mean for a long time I saw the same thing. Ammonia is larger. This is the answer. Can you believe that? Do you see ammonia, hydrogen?
Nitrogen.
Ammonia is smaller.
Nitrogen is larger.
Oh yeah, nitrogen is big. That everyone knows. Nitrogen is a big molecule. Okay, so I mean, very few people know ammonia is smaller than hydrogen. Okay, so they tell us, hey, you remember we want to separate ammonia from hydrogen and nitrogen, all right? So this opportunity. So if ammonia, like you said, is between hydrogen and nitrogen, it got stuck, all right? Because we want ammonia to be separate of hydrogen and nitrogen. If hydrogen and nitrogen both are larger than ammonia, we win the game, all right? So I mean, before I show you the result, if you say the ammonia is larger than hydrogen, that means ammonia will be in between hydrogen and nitrogen, then you never win. So anyway, so this opportunity, we are able to separate ammonia from hydrogen and nitrogen because they both are larger. But the challenge is they are larger, but see, they're so close. They are 0.3 angstrom. What's the angstrom? If you learn the physics, 1 angstrom is 0.1 nanometer. You follow me? So that means ammonia is 0.03. The difference is So did you see that? Did you see the difference? It's 0.3 angstrom. That means it's 0.03 nanometer. It's very slow. I mean, I'm pretty sure when you do the PhD research, or even when you are in college, you heard about nanotechnology. Everyone in the last 20 years and talk about nanotechnology. Now nanotechnology is cooling down for after 20 years. Doesn't matter the cooling down or not, but everybody work on the nano scale. But this is not even sub nano. It's a sub nano. Sub nano means 0.1 nanometer. It's differences. So with such differences, it's very difficult to use the conventional membrane. So conventional membrane means for the water filtration, you can have the ceramic membrane. You can have all kind of membrane. So to design the ammonia membrane, you have to play a little bit trick. The membrane only allow ammonia come in, but don't allow the other come in. But if the error is a little bigger, that means no one will go through. For example, if you make this size, this yellow opening like a 2.5, all three of them will be sitting on one side. But if you make this like a 3.0, and then nitrogen will go through, hydrogen ammonia will stay on one side. Okay, it's very tricky. So that's a little window. So there are some research going on. Actually, I team up with the University of Delaware, a professor. So basically she and I, we basically designed this the ammonia membrane just to do this. The ammonia membrane for this is not going to be ceramic. It's not conventional the silica based molecular sieve. Both those are inorganic membrane. But here we call the polymer carbon molecular sieve. It's called the metal carbon embedded. It's called CMS. So it's basically start from the polymer precursor. You make the fibers. I don't have a cartoon to show you, but I think today is Wednesday, either Thursday, Friday, I may have a half session to show you just how the catalytic membrane is going to work for ammonia synthesis. I just want to show you there's a different way to separate ammonia. Membrane is one option, but it begins with this organic structure. Traditional membrane or the traditional molecular sieve is all start from inorganic material. It's called the silicon or the silicon carbide, okay, or the even ceramic or alumina base. But those traditional technology doesn't apply to here because they cannot regulate the size differences plus minus 0.03 nanometer. Make sense? Everybody understand? Question?
Sir, can we produce the membrane using additive manufacturing technology? Because it is ceramic, we can't do those things in additive manufacturing.
Yeah, ceramic you can do basically a variety of things because it's inorganic material. But polymer you have to make it into the carbon fiber, hollow carbon fiber. Maybe I can show you a picture. Okay, so basically you start from organic structure, you do pyrolysis and form the carbon fibers. Let's do this. We are going to come back here. Okay, so let me see we are going to come back to this slide, but I want to show you how this membrane looks like. It's not like this. Okay, this is really too ideal. You have, but the carbon fiber or the CMS membrane is more like you have a lot of the fiber filament, like built together. Okay, so give me the 1 second. I will show you. Okay, I'm going to stop sharing, and then we will come back to that TA. Hold on. Yeah, I need to show you the structure of the material. Okay, let me share the. Okay, I'm start sharing. Can you see my slide? So it's basically, even if I show the conceptually like this, you have 2.9 angstrom opening, and then only allow the ammonia molecule come in and leaving hydrogen, nitrogen on one side. The real membrane actually is more like fiber. Do you see this? More like I would say you call the birdhouse, is that right? So basically you have bundle of the fibers, and then all together. You bundle them together, stack them together, and then the opening of when the molecule going through the opening is like 2.9. So that's how they build the so-called CMS and membrane. So look at this, it's more like birdhouse. They say stack them together. So you actually, what should I say? Let me see now if I have, where's my, your gas flow direction will be like this. Okay, so you gas flow direction passing with all these fibers, and then all this the fiber, the opening is the design. You can basically you can design these fibers and then allowing the gap or the penetration on the fiber. The gap is 2.8 and let's say 2.8. Only ammonia coming through, but 2.9, 3.6 will be staying on one side. Okay, so this is the gas flow direction. And this cartoon really shows you how the CMS membrane separation it looks like. It's more like birdhouse. Okay, so I'm going to stop sharing and then going back to my presentation. Okay, so let me see. Where is my? Okay, so I think we are here. All right. So now, okay. So the one more thing. So there's another regeneration method. It's called a cryogenic flash separation. Let's read this. Okay. So this is another low pressure separation. It's called a cryogenic flash separation. You have to chill the hydrogen, nitrogen, ammonia, use cryogenic, but it's not high pressure. It's different from Haber-Bosch cryogenic condenser. Here, you basically chill the vapor. And read this. This cryogenic flash separation refers to a process where ammonia vapor is rapidly cooled to a very low temperature. So it's different from a cryogenic condenser, which is under pressure and the temperature. Here, you don't need to, because low pressure, we don't have to touch the pressure. All we care about the cryogenic, but it's very cold. Typically, people use liquid nitrogen and then chill the gas phase because ammonia in gas phase. When you chill the gas, the vapor, ammonia condense, but you will never condense the nitrogen and hydrogen because it takes even much the higher temperature, much lower temperature. So then basically they are hydrogen, nitrogen, and ammonia. They have different boiling point, all right? So with the vapor phase containing lighter component, quickly separated from the heavy is ammonia. That's called flash in there. So what does it mean? So everything in the vapor phase, all of a sudden you chill the whole thing under ambient pressure, and then ammonia condense, it's called flash, and the nitrogen and hydrogen will be gone. So this also can be applied to the separation of ammonia. Okay. So anyway, until this point, I introduced you with you so many separation technologies, and all we have been talking about all of this yellow, okay, technology. So you may be wondering what's the result. We have so many case studies. Case 1, case 2, case 3, even under case 3, we have a different sub cases, 3A, 3B. I don't want to go through, but I want to show you the result. Then we talk about techno-economic analysis and how powerful this is the low temperature microwave reaction combined with the low pressure separation of all different cases. Our baseline is Haber-Bosch. Okay. So here's the key result. So remember we have the different cases. Okay, case 1, case 2, case 3, which we went through already. So this also tell you case 1 is cryogenic flash separation. Case 2 is membrane separation. Remember that's the ammonia membrane. And also at the beginning today, we talk about the vacuum TSA, thermal swing operation. So then, and case B, vacuum TSA, and case 4, and then it's the little bit of pressure PSA. So and then if you look at total reactor volume, all this yellow highlight is the condition. Okay. So anyway, so this is one of the result we got from all this simulation, and then we have the ammonia mass flow. in the recycle loop in here. So in these two cases, you do have ammonia in the recycle loop, but in here you don't have ammonia in the recycle loop. Okay, so all these are the data and assumption, but it's not an economic result. It's really a technical result. We are talking about techno-economic analysis. These assumptions, when you do techno-economic analysis, you have to make assumption. Okay, so for example, reactor inlet temperature is set at 320 degrees C, and the reactor inlet pressure, and then what you want, the purity of ammonia. Remember, the higher the purity, the more the challenge on separation. So that's why the farmers go to sulfuric acid. They don't care about the ammonia. They just sell fertilizer. But if you sell as ammonia 99.99, which is high quality ammonia, you have to do a lot of simulation. Then we have the flow rate of ammonia in there. So all these assumptions are factored into the TA. So again, so the feed we also have feed compression. All this is the data. Here's some definition I want you to understand from the techno-economic analysis. AD means annualized direct cost, or it's called capital. Okay, so I'm going to interpret to you. And UC means the utility cost. In the ammonia synthesis, you have the recycle pump, the compression and the heating and the cooling. All right, all these are utility costs. It's called OPEX, operating cost. When you build ammonia plant, you put in capital. All right, so the capital has to be depreciated. So let's say you spend $1 billion. Next year, your plant is not going to be $1 billion. It's going to be $0.9 billion. So that's a $0.1 billion is called depreciation. That's your cost, because you start from brand new plant, and after 20 years, so you basically, there's no value of your plant because I will depreciate. That's capital cost. So I'm going to pause here, and then I want to make sure you understand the terminology. Does everyone understand the annualized direct cost, which is the capital cost? Anybody understand? You understand, right? Okay. And the operating cost is very easy, the utility. For some the defendant you major, if you never learn this, your annualized direct cost is very difficult. But I try to simplify for this for you. If you put so much money, $1 billion, after 10 years or 20 years, the value is gone. But over the year, when the value decrease, that's called your cost. Is all right? Why is the cost? It's more like you buy the brand new car, and after a couple of years, the value decrease. So your cost will be the depreciation. So this is called annual capex. Okay. So anyway, let's go to the result. So this is from TA, ammonia synthesis process, and an economic summary. So in base case, remember base case is the what's it called, Haber-Bosch case. There's utility cost, there's the depreciation cost, and then on the case 1 and case 2, case 4, there's the utility cost and also the depreciation cost. Okay, so overall, you're adding the utility cost and the depreciation cost. Haber-Bosch is more expensive. Do you see that? The bar are much taller than this. But if you look at the detail, the breakdown, so actually the Haber-Bosch capital cost is not that bad. It's actually lower than the other two. But the problem is operating cost. Why operating cost? Because they use cryogenic separation, high pressure, and also they have a condenser. All right. So that's why the new technology are the much lower. So question. I'm asking a question, then I will let you guys go for today. We will continue tomorrow. Okay. So. Can you read my question? Anybody that can answer my question? Why Haber-Bosch process, base case here, the capital cost is lower than the other two? Overall, the other two cases are much better. The total cost are much better than here. The bar of a base case is much taller. But if you look at the breakdown, actually I would say the capital expenditure of base case is not higher than the other two. So why?
Sir, it's a thermal process and it can be scalable to larger amounts. Production is higher.
Yes, it's called economy of scale. All right. Hey, remember from the day one, we keep on saying Haber-Bosch plant is built so large. All right. So when they build so large, that means the per capita cost is lower. But all of this is we basically put them on the same basis. Okay. So the capital cost is lower because they built so large. Remember, I show you the so-called 0.6 rule. Scale down Haber-Bosch to the low, this is the smaller production is not economic feasible because you're here and it'll be higher. But even with the microwave, we already improved the capital, but still, you look capital is higher. We spend so much of the effort running microwave or chemical looping or electrochemical. The idea is to lower the pressure, all right? And then by lowering pressure, all the recycle loop. Let's go back to the beginning. So that's that's major innovation. So by lower the pressure, all this downstream, the capital, the operating cost increase. The capital may not be necessarily increase, but operating, because we don't need to use the compression. We don't need to use the cryogenic condenser. All the downstream, you can use the solid solvent. So the operating cost decrease tremendously. Okay, so if you don't remember this, the Haber-Bosch, they have so much utility in here, whereas the low pressure, you don't have too much utility. Make sense?
Yes, sir.
Okay, so that's the whole idea. So I think all we have been talking about in the last 8 days is just start clicking. So you have to look at today we are talking about system engineering. Okay, system engineering is we should not just look at the solid solvent. We should not just look at the microwave reactor. We have to look at the overall the plant. So where are the savings? Okay, so the savings actually are on the utility cost. Okay, make sense?
Yes, sir.
I'm going to show you one more graph, and then let me see how many slides I have. I still have a lot of slides. Economy, but I'm going to show you this. Okay, so I'm sure you understand this graph. All right. So basically, the new technology outperform Haber-Bosch not because of capital, it's because of utility, because the downstream separation is really become efficient. So let me show you one more pie chart on the breakdown of the cost items. Then we just we finished today. Okay. So let's spend some time. I want you to read the 3 bullets. Then I'm going to interpret this the pie chart for you. Again, there's a different angle to look at the base case versus case 1, case 4. Whereas here only summarize the utility cost and capital cost. Okay, but that's utility cost and capital cost is not just the technical economic analysis. Technical economic analysis has some other features, which is here. Okay, so read the bullet point, and then let me interpret to you. So basically, for each case, they normalize into 100% just to compare as a percentage the pie chart. Where are the major costs in there? Okay, so let's see the other. So case 1, case 2, case 4, they both are microwave, low pressure operation. Let's see the case 1, how case 1 compare with the base case. If you look at this orange color, it's called the feed compression, all right? UC, utility cost. It's 45% Haber-Bosch. Why? Because you recycle, you have to recompress it and recirculate. So in Haber-Bosch process, baseline, 45% of the cost are on the compression. But come to the case 1, you see all these color coded are identical. Look at feed compression cost, 5%, right? That's the advantage of microwave because you do not need to compress the gas because you are lower pressure of it. Why you need compress it? Your separation doesn't need it. Okay, so this is really major improvement. But as a percentage, so what's the cost? Well, reactor synthesis. Okay, the capital because it's a microwave reactor. The capital is different, and also the small scale. Of course, the capital is different from the reactor synthesis, which is 18%. In the Haber-Bosch process, the process, the reactor, the Haber-Bosch reactor only 18% overall. But here in microwave, it's almost 40%. So the majority of the capital costs are in the reactor, but we save a lot of compression costs. Okay, so now let's maybe look at the other one, the different color. Okay, so keep in mind that feed compression, there's a operating cost. Feed compression also has a capital cost. You remember, you have the recycle pump, you have compressor, you have condenser, all right? So all these are associated with feed compression. It's quite a bit of money, but true. In the Haber-Bosch, yeah, in the microwave, it's about the same, the breakdown. Okay, so which is good. So another big difference is the yellow part. Reactor synthesis utility cost in microwave is 23%. Here's 13%. Why microwave has more utility cost in reactor? Haber-Bosch process, ammonia synthesis is isothermic. Isothermic means you basically once started, they give out heat, all right? But provided you have to keep reactor at 500 degrees C and 250 bar. So now in the microwave reactor, the reactor synthesis is 23% of cost because the microwave we are operate at a lower pressure, low temperature. You have to use the microwave. Remember selective heating to activate nitrogen. But here in the Haber-Bosch, you use the pressure and temperature. That's all. But here it's low temperature, low pressure. Pressure temperature doesn't help you to activate nitrogen, but you have to use the microwave. So that's why your expenses are high. So anyway, somewhere the basic. So tomorrow we are going to probably come back revisit. We are going to compare case 4 and the base case. But regardless, by comparing where are the savings of the new cases, you know where to do the innovation. All right. So a big innovation is feed compression. So feed compression is very low. So look at it. So you to say different way, in order to improve any chemical process, doesn't matter Haber-Bosch, doesn't matter refining process, you have to understand where if you have room to improve. Of course, now for Haber-Bosch, we have room to improve because 45% of cost are feed compression. So we lower the pressure, right? We use a new technology in downstream separation. So we save this money. So this 45% become 5%. So you have to really identify where the saving. Then you introduce or do the innovation. Okay. We have maybe just 1 or 2 minutes. Any questions until this point? Technical economic analysis.
The plant size is higher in HP process, so it's add up the cost. Plant size is very high.
Yeah, you're right. HP part. So keep in mind, this really the normalized. This not comparison of for the absolute dollar amount. It's not like a dollar amount. This is really on relative basis. If you look at this pie chart, relative, where's the basic the capital spending, where utility spending on it? Okay, I mean, tomorrow we are going to talk about on the absolute basis, how much is it going to cost to produce 1 kg ammonia from Haber-Bosch? How much is it going to cost to produce 1 kg from the new technology? That'll be tomorrow, okay? So because I do have some slides, but here just to tell you, what's the advantage of the using microwave? Where are the innovation and the savings? Well, savings is here, orange color, all right? But true, there's nothing is perfect. The downside of this, that increase the what do you call that? The capital expenditure on the new technology. Okay, so this is on relative. I think there's someone just say something in the background. You're right. Haber-Bosch process, it's large. It's very difficult to beat. So I think the microwave we try our best. At least we basically we don't need the feed compression utility. Make sense?
Yes, sir.
Any more questions?
No, sir.
Okay, so we end for today. So tomorrow, again, there will be 3 sessions. And then tomorrow, I'm going to finish the TEA and talk about the, again, clean hydrogen generation. It's not renewable. Green hydrogen means you use renewable power to generate hydrogen. And then the blue hydrogen means you use natural gas to generate hydrogen, but you have to inject CO2 capture in the underground. It's okay. You can use the blue hydrogen. It's called blue ammonia. So tomorrow I'm going to talk about different color of the hydrogen. It's somewhere between blue and green. It's called turquoise hydrogen. That means we produce the hydrogen using natural gas, but without generating CO2. So that's another clean hydrogen. So remember in the first day the lecture, green ammonia, or doesn't matter what kind of ammonia, it's all about hydrogen. If you secure hydrogen price, you win the game. Okay, so tomorrow we'll finish this, and hopefully we can get in the hydrogen production. I may have one quick case study and for the student. Okay, so I will see you tomorrow. Thank you.
Thank you, Professor. Thank you for the perfect session. We'll send you the link and we can meet you tomorrow.
All right. Okay. All right. Thank you.
Okay.